Hi everyone! Today we're going to talk about how to select an appropriate base for an acid-base reaction. So previously we talked about how to identify the most acidic proton on a molecule. So now we know how to identify the hydrogen that will be donated during an acid-base reaction. But how do we pick a good base? So let's draw the generic acid-base reaction that we've drawn before. And let's assume there's equilibrium here. And we know that our products will be the conjugate base and the conjugate acid. Oops. All right. So in this reaction, we want to make sure that we have a base that is strong enough to deprotonate the acid, but also will push equilibrium to the right towards the products. So let's write that down. Okay, so in order to kind of figure out what a good base would be for a reaction like this, we need to talk about pKa. So we already reviewed Ka values and pKa values, but remember that Ka values are acid dissociation constants. So those are equal to the concentration of products over the concentration of reactants. And if you have a really large Ka value, that means you have a strong acid. So looking at our expression for the Ka value, if that value is large, that means we have a lot of product. So a large Ka value also means that equilibrium is to the right. However, as we've seen previously, some Ka values are very large and some are really small. So it's easier to use a pKa value. And the pKa is equal to the negative log of the acid dissociation constant. And so remember that we're kind of flipping our scale here. So a large Ka tells us we have a strong acid, but if we convert that into a pKa value, we actually have a small pKa for a strong acid. All right, so the smaller the pKa value, the stronger the acid, and equilibrium will go to the right towards products. All right, so that being said, we want the pKa of our original acid in the reactants to be smaller than the pKa of the conjugate acid in the products. So our conjugate acid should be really weak compared to the original acid. Now, the reason for that is, remember, a strong base is going to produce a very weak acid. So let's just quickly write that down as kind of a review here. And remember, a weak acid will have a larger pKa value. Okay, so that means we want the pKa of our original acid. That should be smaller than the pKa of our conjugate acid. So our original acid has to be stronger than our conjugate acid, and that's because our conjugate acid is coming from our base, and we want the base to be really strong as well. Okay, so everything's related to each other here. So let's look at an example of how this would work, or what this might look like. So let's pick an acid, and I'm going to pick acetylene. Now, acetylene isn't the strongest acid. It's actually a pretty or fairly weak acid. But we have seen this molecule before where we have two carbons. They have a triple bond, and then each carbon has a hydrogen attached. And its pKa value is, well, let's look it up. So on Canvas, under the module study guides, I have something called the Evans pKa table. So this is 2 pages, or sorry, no, not 2 pages. There's multiple pages here. And you can look up the pKa of common substances. So you'll notice that on the first page we have the pKa of inorganic and oxo acids. So those are acids with nitrogens or different metals or sulfurs, etc. Then we have the pKa's of nitrogen acids. And then we have the pKa's of CH bonds in hydrocarbons and carbonyl compounds. And then we can keep going. So there's a lot here to digest. So we're looking for, again, acetylene. So let's see if we can find that. Let's see. So we've got here it is. I'll mark it up here. All right, so if we go to the third page, where the hydrocarbons are, it's located right here. So we have HCCH, so that is acetylene. And its pKa is listed as 24. Some tables will list it as 25. It doesn't really matter. Either one's fine, as long as it's somewhat close to the actual pKa. Okay, so let's go back to our PowerPoint, and we'll write down that the pKa of acetylene is 24. All right, and then let's say we have some generic base. And then that base takes a hydrogen, and we leave behind a lone pair on carbon. And then we have our conjugate acid. So remember, we're really curious about the pKa of the conjugate acid. We want that to be larger than the pKa of the original acid. So the pKa of the conjugate acid should be greater than 24. Okay. And if you want to practice these concepts a little bit more, I recommend the Skill Builder 3.11 exercise on page 118. But let's go over some more examples together and make sure we understand what's going on here. Okay, so let's use the example of acetylene again, but this time we'll actually pick a base that we know really well. All right, so let's pick sodium hydroxide. That's a really strong base, right? Okay, so remember that the sodium in sodium hydroxide is a spectator ion, so it's not typically going to react or do much. So we're really just focused on the hydroxide ion, but we'll just write that it's coming from NaOH. Okay, so our base is going to grab onto one of the hydrogens, and then we'll leave behind a lone pair of electrons. And now our conjugate acid is water because OH grabbed onto another hydrogen. And I'm just drawing the lone pairs there for consistency. All right, so we said the pKa of acetylene is 24. Now let's go look up the pKa of water on that table. So I think we need to go, oops, we need to go up to our pKa of inorganic and oxoacids because we know there's oxygen in this molecule. And actually, water is listed right up top, and its pKa is 15.7. All right, so let's go back, and we'll write that down. Okay, so if our pKa of the conjugate acid is smaller than our original acid, is hydroxide a good base for this reaction? No, so hydroxide would not deprotonate acetylene very well. So the pKa of the conjugate acid is small or smaller than the acid. So the base is too weak to deprotonate acetylene. So again, remember, because water's pKa is smaller, that means that the base isn't very strong. If we had a strong base, it would produce a really weak acid with a really high pKa value. So hydroxide just doesn't quite cut it here. We need something different. Okay, so maybe let's look up something with a really high pKa value. Okay, so, oops, I keep forgetting to turn off the marker. Let's see. Actually, what about ammonia? So ammonia is a base. It has a pKa of 38, so that's a lot higher than the pKa of acetylene. So that could be our conjugate acid, and we'll figure out what the base would be from there. Okay, so let's do that. So our second example, we'll use acetylene again. And again, its pKa is 24. Now this time we want to end up with the conjugate acid NH3 because its pKa is 38. And that's much higher than 24. Now NH3 is already a base as it is. So how could we make it even more basic? Well, we could remove one of the hydrogens there and use this base, NH2, and this is a super strong base. Compared to the hydroxide ion anyway. Okay, so in this reaction, we know that the lone pair will grab onto hydrogen. We'll leave behind a lone pair on carbon. And we end up with a conjugate acid of ammonia. And ammonia has a pKa of 38, which is a lot higher than our original pKa of the acid. So that works. Okay, so we found a base that will deprotonate acetylene. All right, so the pKa of the conjugate acid is larger than the acid. So the base is strong and it can deprotonate. Also, in this case, equilibrium does lie to the right. So we will go in the direction of the products, whereas in our first example with the hydroxide ion, equilibrium would actually lie towards the left, towards reactants, because the stronger acid is on the right-hand side. So in general, you want to choose a base with a conjugate acid whose pKa is 5 units higher than the acid's pKa. So the pKa of the weak acid should be greater than 5 units higher than the original acid pKa. All right, so let's do a practice problem. Now, in this practice problem, we're going to combine a lot of the ideas that we've already seen. So first, let's decide which hydrogen on our molecule is the most acidic. And then let's pick a base that will deprotonate the acid. Oops, deprotonate. All right. Now, actually, I'm going to rephrase that a little bit. We want a base that will deprotonate only the most acidic proton. Okay. So a bit of a distinction there. We don't want the base to deprotonate any of the other hydrogens, just the most acidic one. All right, so our molecule that we're looking at is this one. We've got 1, 2, 3, 4, 5 carbons, and then we have double bonds to 2 oxygens. And the hydrogens that we're comparing are the ones in the middle here and the ones on the end. Now, the hydrogens on the far right of the molecule are the same as the hydrogens on the far left, but we're just going to show the ones on the right for now. All right, so these hydrogens are different because they're in different places, so I'm going to highlight one set as yellow, and I'll highlight the other one, let's do purple. Okay. Now we're going to again follow what we did before in previous lectures. We're going to determine what the products are when we lose a purple hydrogen and what are the products when we lose a yellow hydrogen. Oops. There we go. All right, so let's highlight those. And I encourage you to pause the video and try this on your own first, and try to see if you can figure out which hydrogen is more acidic. Okay, so let's draw the products, or the product that we would expect if we lost a purple hydrogen. So if we lose a purple hydrogen, most of the molecule stays the same, but we'll have a lone pair of electrons on that far right carbon. Okay, and then what's the product if we lose a yellow hydrogen? So again, it will look pretty similar, except we'll leave a lone pair of electrons on that central carbon. All right, so now we need to go through cardio and figure out which of these is more stable, which of these conjugate bases is more stable. All right, so let's go through C, charge. So the charges are the same. They're both negative. So next is atom. Both of those negative charges are on a carbon. So then we go to resonance. Okay, so looking at the product for the loss of a purple hydrogen, are there any resonance structures? Yes. So notice that we do have a lone pair next to a single bond, next to a double bond. So we can, move this lone pair over to create a pi bond, and then we'll move our pi bond up to create a negative charge on that oxygen. Okay. Now, is there anything else we can do? Any other way we can move the electrons? No, not really. So these would be our two resonance structures for that conjugate base. Okay, and what about our other conjugate base? So if we lose a yellow hydrogen, do we have any resonance there? Yes, in fact, we have two different ways that we can form resonance. So you'll notice that this lone pair is next to two single bonds, and each of those single bonds is connected to a pi bond. So we could move the electrons over to the left or to the right in this case. And either way, we're going to move pi electrons up to one of the oxygens. So this structure should have three total resonance structures. So I'm actually going to erase this chart here so I can make some room. Okay, so if we move the lone pair over to the left, we get this structure. And if we move the lone pair to the right, we get this structure. Okay, so these look pretty similar, right? They just look like mirror images of each other. But remember that these all form a hybrid structure. So the negative charge is shared between the two oxygens and the carbon in the middle. So we do want to show all of these structures. All right, so let's draw brackets around those. Okay, so which conjugate base is more stable? The one on the bottom, right? Because there's 3 resonance structures versus only 2. Okay, so that tells us that the yellow hydrogens are the most acidic. Great. And if we look up the pKa values for these different hydrogens, the pKa value for the yellow hydrogens is approximately 9. And the pKa values for the purple hydrogens are approximately 19. And remember, a lower pKa value means a stronger acid. So the yellow hydrogens are more acidic. All right, so now that we've identified the most acidic proton, we need to find a base that will deprotonate only that proton. Okay, so we want something with a conjugate acid that is between 9 and 19, or the pKa is between 9 and 19. So here, I'll write that down below. And actually, we did see an example of this earlier in the lecture. We did see a conjugate acid with a pKa between 9 and 19. Which one was that? Water. So water has a pKa of 15.7, and the base was the hydroxide ion. Okay, so we can use the hydroxide ion as our base. Oops. All right, so the base here will be OH minus because the conjugate acid, the conjugate acid pKa is between 9 and 19. So what that means is that the hydroxide ion will only deprotonate a yellow hydrogen. It can't deprotonate the purple hydrogen. We would need something with a larger pKa value for that. Okay, so I hope that helps to better understand how we choose a base for a particular acid. We also saw this example in particular where we had 2 different types of hydrogens and we needed to pick a base that would only attack one of those hydrogens. All right, so in the next video, we'll talk about how to select an appropriate solvent for your reaction, because a lot of the time we have to dissolve our acid and our base. So how do we pick a good solvent for that? So I'll see you then.